All right. Hello, everyone, also from my side. My name is Patrick, and I'm the team lead of the threat analysis team at VMware. To be honest, I won't really introduce myself because this is usually a very boring story. Instead, I would like to start a bit differently today, and I would like you to just imagine you're being a person that is responsible, or part of a team that is responsible for the cybersecurity in an organization. And you just go to work on a Thursday morning. Everything seems to be regular, everything seems to be fine, nothing is happening, you don't see any kind of alerts. At the same time, a threat actor is actually also going to be active and coming up with a new malware family that is just getting around the world in the end. But you still don't see any alerts, right? And somehow, unfortunately, they're managing to walk just past you, to walk past your security solutions, your security measurements, and you still don't see any alerts. And at a specific time, maybe a couple of hours later, or maybe even a couple of days later, you realize that something in your network starts to behave strange or differently. Maybe users are going to report that something is wrong, they can't use their machines anymore, because in the worst case, there is just a pop-up message on any desktop saying that this machine has been infected with ransomware. And this, of course, is probably one of the worst nightmares that to security folks, as we all are, can happen. And unfortunately, this seems to be case, or this seems to have happened with a malware family which is called Pikabot in the past. And I think we are here to just share our stories, share our expertise, and also share our knowledge to just empower the community to be strong for the future and avoid such situations, of course. So in today's talk, I would like to focus about Pikabot, about its evasion techniques, in particular about indirect syscalls. But before we dive into this specific topic, let's provide a quick overview on what Pikabot actually is. So it's a malware family that has been appeared in early 2023, so it's relatively new, it's 1.5 years old. It's classified as a loader or a downloader, which means it's supposed to infiltrate networks, get persistence there, and in future stages just download additional payloads and executes them. The threat actor that this is related to is known as TA577, which I guess probably all of you have already heard about them. They are responsible and well known for distributing QBot or Quackbot in previous years, and they were very, unfortunately, successful with it. QBot has been shut down, so essentially they needed to search for replacement, and this is then when Pikabot came into place. They are also known for distributing blockbuster ransomware and making quite a good amount of money with it, which also highlights how important this actually is and how serious this threat is going to be. Yeah, and Pikabot is known for its evasion techniques. It doesn't only contain evasion techniques, it also contains obfuscation, just everything that makes our lives as reverse engineers, as analysts, as security analysts, anywhere, way more difficult. And one part of this actually is indirect system calls. Taking a bit of a closer look to understand what we're going to talk about, Pikabot consists of two different modules. On one side, we have a loader, and on one side, we have the core module. The loader is basically responsible for just loading the core module, and as the core module is essentially the heart of this malware family, it also is protected in some special ways, and the loader is responsible for unpacking the stuff and then basically executing the core module. The core module, as its name, is responsible for everything else. It's doing command and control server communication. It's responsible for injecting additional payloads, doing command execution, but also doing some data collection, actually fingerprinting of the infected system. So you may wonder why we actually even talk about Pikabot, because in 2024 it went dark, so it was basically shut down due to Operation Endgame, which was a huge law enforcement tasks that just killed a couple of different botnets, and Pikabot was one of them. Even though the malware family itself is dead, this doesn't really mean that the techniques and all of the nasty stuff that they've implemented there is dead, right? So the techniques that they have used, they are still alive and they will be used by other threat actors and in other malware families as well. So I think this is actually quite a good example why we still need to talk about this. And we also probably expect there are some additional threat actors coming up, picking the same techniques, maybe advancing them even more, extending them. So we should still be aware of what has happened there and what might be happening in the future. And this brings me actually to the evasion techniques. So we will start now covering a couple of them that we have seen. We still wait a bit with indirect sys calls before we actually dive into the fun part. So a couple of them that we have highlighted, and I think those are relevant and interesting anyways for also other malware families. And one is the hardware-based evasion technique. So this is actually not new at all. We know those are there for some years. And also usually just checking for resources to determine whether the malware is running on a virtualized, maybe analysis environment, or if it's running on a real machine. Usually those checks are actually quite funny from my point of view, because they are checking for if the system has more than 2 CPU cores and if the system has at least 2 GB of memory. To be honest, this isn't really telling anything, because I don't know if it's even possible nowadays to buy a machine that has these hardware specifications, right? Even smartwatches have more than this. So those checks are there for years and they have never been really touched. But we do see actually a trend since this year that those checks are getting adjusted as well with the time being. So instead of checking for 2 CPU cores, they start checking for 4 cores, and instead of 2 GB memories, they also start for checking for 8 GB memory, which is still probably not really a very, very difficult check to detect, and also not very difficult to get around it, but just we need to keep in mind that threat actors slowly starting to also adopt basically with the time. Another check we have is the language-based evasion. So essentially, this is also nothing new at all, but it's still important to highlight this, and we see 2 different use cases for these language-based evasion checks. Well, it's maybe not even a full evasion check, but it also has some different purposes in the end. So on one side, this can be used to target specific countries, specific languages, basically. In the keynote, I think yesterday from Robert, from Asset, we have seen that this banking Trojan he was talking about was mainly targeting Latin America-based countries, right? And this can, of course, be done via languages, for example. There are lots of different artifacts on a machine that you can use. So you can target a specific group with them. And the second option that this can be used for is, of course, to avoid infections in specific countries. And this is also what we see usually in some of those malware families, especially if they have been developed in former Soviet Union countries like Russia or anything like this. Then they usually avoid infecting devices in their own countries, because this also prevents them a bit from law enforcement on at least their own country. So this is the second option why this is often being used. Then we have timing-based evasion. Well, that's also nothing new, right? We all know that doing some sleeps, waiting on some specific events or actions has been used for years. The main goal for this is just to pause the sample execution as long as possible to maybe avoid a successful detection either in a sandbox or in an emulator. However, for Pikabot, we have seen something that is kind of new, and this is the use of a quite uncommon API, which is called Beep. So Beep is a Windows API that's essentially supposed to make a beeping noise on your computer, and it's blocking in the end, right? As long as this noise should appear, basically, it's just doing nothing. Unfortunately, we weren't really able to get this beeping noise out of any machine, so it looks like the API is also quite old and doesn't really work on modern systems anymore, but the API call itself still works, right? So it just takes 2 arguments. You have a frequency and you have a duration, and if you set a duration of like 10 minutes, for example, this API call will just pause the execution of the sample for 10 minutes, maybe used to get past some security tools. And this is kind of new because we haven't seen Beep being used before, and if you're not mistaken, Pikabot in its early days was also called as Beep Loader, or was also referred as Beep Loader, which is basically based on this API call. And another check, which of course is also something that we see commonly, is checking for sandbox or emulators. In this case, they made use of trying to load fake files. To be honest, this doesn't really affect sandboxes. There might be some exceptions out there, but emulators, I think, are usually more affected by this one here. So essentially what they're trying to do is saying, well, please give me, or I want to open file which is called foobar, whatever, and a regular system would say, oh yeah, sorry, this file doesn't exist, so I can't open it, it's just an error, right? On an emulator says, well, oh yeah, you probably need this file to run successfully, so here it is, please take it, even though it doesn't exist at all, right? So this can also be quite easily used to detect some of those emulators or some sandboxes probably. And then, of course, finally, we have the interesting part, and this is the monitoring or hooking-based evasion via indirect system calls. And this is, of course, where things are getting funny, exciting, and also a bit more technical now. So before I will jump into this topic, I have two disclaimers here. First one, of course, there is a certain complexity around this topic, and within 45 minutes it's quite difficult to explain all of it. So we probably have removed some of the complexity here to just save some time, and you might encounter that some information might be missing, but this is hopefully on purpose at least. And the second one here, about this whole story of direct and indirect syscalls. I mean, there's a lot of discussion going around in the community. There is also a certain confusion whether something is being referred as direct syscall or something is referred as indirect syscall. There's also where opinions are actually going into different directions. Based on what we are presenting here today, this is on our own experience, and this is also at least how we understood this whole topic. There might be some people disagreeing with some parts, but I'm of course happy to also take some discussions afterwards on this. Yeah, before we start, we of course need to look a bit into the Windows API to understand what is happening. So we have this little chart here that we will probably see in a couple of slides now, maybe even through the rest of the presentation, where we just see a bit this control flow, execution flow, on how to get from an API call to basically kernel code execution in the end. And this is how it should look like, or this is how it's expected to look like on Windows systems. So we have here on the left side a user mode, we have on the right side a kernel. We're actually not really interested in what the kernel is doing, we're only interested in what this path is from user mode to kernel mode. And over there we have a sample that is being executed somewhere in the process, and it just has some instructions in it. And at a certain point it wants to create a file. This is just a demonstration API call, could be anything else, but we say we want to create a file. So usually what is going to happen here, you make use of the Windows user mode based APIs, which has an API function called createFileW, which then refers to, and this is where the first complexity has been removed, usually to kernel32 DLL and then to kernel base DLL, but as this is usually just a redirection due to backwards compatibility, we just have removed this step. So we're somewhere being in kernel base DLL, where this API is implemented. It has some instruction, maybe doing some checks, doing some validation. And then it continues and calling the native function for it, which is then in NTDLL, which is called NTCreateFile. So this is usually the lowest level before the kernel mode execution is going to happen. So we have some instructions here as well, and at the end we do have this syscall instruction, which just indicates to the CPU, well, now we want to switch from user mode to kernel mode because we are performing an operation that requires higher privileges. Creating a file, you need to touch the hard disk, you need to maybe access some drivers, resources are managed by the operating system itself, by the kernel, so basically that's why we need it. Once this is done, once kernel has finished execution, all the way is actually just going to be back up where we came from. So this is how it should look like. As modern systems, or usually all systems in organizations, are having some sort of antivirus installed, maybe also even having some EDR systems running, they are starting to monitor stuff that is happening, right? And of course, there are different complexities on the systems. They have different ways of being implemented. They also sit on different locations. At least for our talk here, and this is just a very, very simple demonstration, we said we have an EDR indent hook on any of those user mode APIs. So as an example here, we still starting with the same example. We have createFileW. It's going to kernel base, and for example, in kernel base, you can see a jump instruction instead of the code that we've seen before, which then just redirects to the EDR itself. The EDR then has the capability to look into this API call. It can monitor it. It can walk through these arguments that have been provided. It can scan them. It can scan buffers, whatever it wants to do, and can then decide whether it wants to continue the execution or blocks it because this seems to be dangerous. In this case, we are continue, which then just continues the execution. We are going back to NTDLL. We're having the syscall, and we're going to the kernel in the end. Just for sake of completeness here, this EDR hook would likely be somewhere probably in NTDLL because it's the native function. It's lower to the syscalls in the end, and there are also less functions available in this. But keep in mind that this is just a very basic example. So, of course, threat actors want to get around this problem because this is usually very annoying for them to get detected. So what can they do? And there, of course, are very much different ways. And one way is, instead of just using basically the existing kernel base that has been loaded during process startup, where the EDR actually also implied is hook, is just to load a fresh copy of it. Those EDR hooks are usually indent hooks that only affect DLLs that have been loaded into memory already. So instead of using this one, you can just replace it with a fresh copy of the file, and then you basically would be gone. A different story, it could also just pass it and try to find those hooks and then just batch them out. It's also just a very simple way. Same, of course, applies if the hook would be an NTDLL. You can just replace it in the end or load a fresh copy. And then we would go there, we have the syscall, and the EDR, at least if it's a user mode EDR that relies on hooking only, would be blind in this case. A good story about this, we are usually already in a time where hooking-based EDRs are, I think, quite rare, and they usually at least rely on multiple different indicators and not only on user mode hookings. Well, so now it's a question. We have those APIs from kernel 32, from kernel base, and then we go into the native stuff, and then we have the syscall. So what's even the point of using all of those APIs in between? Why can't we just use native functions directly? So for Fedektof, of course, they do it already, and this is something that we see quite often. Even though Microsoft or Windows specifically doesn't really want you to use them because native APIs are, at least first of all, less good documented. And on the second side, they are subject to change. So it's not really guaranteed by Microsoft that the native API remains to be completely the same. For user APIs, though, it should be the case. But how would this look like if we are going to use native APIs? Well, instead of calling createFileW, for example, we can directly call NT-createFile. And we can jump over this part in the middle, and we go into the NTDLL directly. This is possible because of lots of researchers have done an incredible work here and also still doing this and reverse engineering all of the Windows internals, because you still need to know how this API needs to be called, right? So it's native API, it's already not really ready for official use, basically. So arguments are not really good documented. Some of them are, but at least to researchers that have reverse engineered all of this stuff, those information is already available. So based on this, it would be quite easy. You can just call this directly. You go into NTDLL, and you have basically the syscall to go into the kernel. And this is something that is being used very, very often in malware as well. Yeah. It has the power to maybe bypass some of the inline hooks that are being on higher level APIs, but of course, it still would be catched if the hook is somewhere placed in NTDLL. Just to see or to display and show how simple this is, you basically just need, in theory, 3 lines of code. Of course, this is a bit simplified, but you just need to get a handle of the DLL. You need to get the address of the function you want to call, and then you need to prepare all of the arguments, do some prototyping, and then you basically can use it directly. So it's a couple of lines of code, and you essentially can directly use native APIs. Well, that's the question, and this is now basically a bit of the story, what has happened with all of this topic here from going to direct system calls to indirect system calls. So what would be the next approach, what we have seen in the past that has been used to basically get a bit more in depth here and avoid inline hooking in native DLLs? So isn't there a way to maybe go from the sample itself that's being executed directly to the kernel, so leave out all of the layers in between that are coming from the Windows APIs? And yes, of course, there is. Otherwise, I probably wouldn't have asked the question, right? There are direct syscalls. Direct syscalls are around for a couple of years, and they are being used actively. To know or to understand how those direct system calls are working, we have to look very briefly into native functions first, because native function is usually the last step before kernel code execution, so we just need to understand how those are being implemented and how those work. So for this, we do have a short excerpt here of NTDLL, which is for NT-createFile, which is something that we refer as a syscall stub or system call stub. And this is basically the only code that is in NTDLL for NT-createFile for this function, and it's just 6 lines of assembly code. We have a move instruction at the beginning, which, just shifts around some arguments, some registers basically to preserve some arguments. And then we have another move instruction that moves the value of 55 into EX register. And this is a very important value because this value is the system service number or syscall number or syscall ID, however you want to call it, that tells the kernel later on during the syscall which function needs to be executed. On this machine where we have looked into this, it's 55, so just keep in mind that this value is subject to change quite frequently. If I'm not mistaken, it even changes on minor version of Windows system, not only on major versions. And this is also, of course, one of the reasons why in legitimate software you definitely should not use them directly hard-coded, which you actually should not use direct system calls in the end at all. But for threat actors, usually don't really care, or they just pass those values out before. Then we have another test instruction and the jump not equal instruction. We can completely forget those two here for our presentation here, because this is usually just to check whether this is a 32-bit process or a 64-bit process. And we are only looking here at 64-bit, basically. Then we have the syscall, which transfers the code execution to kernel, and then we basically have a return statement, and that's essentially everything. So this is not much, right? And this is the only thing that needs to be understood, besides arguments that are being passed to this function, of course, to make use of direct system calls. So looking into implementation here, it's also just a very quick example. All the way down below, you can see those couple of assembly instructions that we have just seen in the syscall step before. We are moving the registers, we are preparing the number of the syscall, and then we're just calling syscall. To make this a bit easier to use, we have wrapped this into another function in C, because then the compiler nicely takes care of cleaning up the stack and so on, so we don't really have to deal with this one. But as you can see, it's also only a couple of lines of code, and you can basically make use of direct syscalls. And then, of course, depending on the complexity of your EDR, this might be able to get around this hooking in NTDLL as well. So how would this look like? We basically prepare everything in our sample directly, and we have the syscall instruction, and we directly jump into the kernel, and everything else is basically out of scope. It's not really needed. This was also, I think, quite an effective technique that has been used. Of course, nowadays we are aware of this, and it's also, of course, on the other side, not that difficult to detect. So if you remember, in the beginning, I have shown this whole path basically from the sample to kernel to NTDLL, to kernel base to NTDLL, and then to the kernel itself. So all of those different DLLs have different addresses, we have different regions, and inside the kernel it's actually usually the case that you're coming from NTDLL into the kernel, and also the kernel returns back to NTDLL. So in this case, we're actually coming from a completely different region, from different symbols, and we also go directly back over there, which also means that it's quite easy to detect this in the end. As an example here, you can make use of the Windows event tracing. You can install some callbacks there. There's a nice way you can have a callback on every syscall instruction that's being executed. It provides you some insights on basically where it comes from, where's the return address, and so on and so forth. And that's quite easy just to figure out from which location the syscall has happened and where it's actually going to return. So this is quite an easy way on how to detect this. And this, of course, then raises the question, is there something else that we can, or that threat actors basically can make use of to get around this problem? And yes, of course, there is, and then this is the point or the time where we actually come into indirect system calls. This is just another way on how this, in the end, can be used. We're having the same setup here, basically, but instead of calling the syscall instruction directly from the sample itself, we are just making use of a jump instruction and jumping somewhere into NTDLL, into the NT-create file function, for example, where syscall instruction is being located. So we're just making use of existing CPU instructions somewhere else to make this whole execution flow look like more legitimate. And this is, of course, also something that we have seen. It's being used in the wild, and especially in the beginning, it worked quite well. Of course, there are some different ways here how you can do this. You can maybe jump to the specific offset for NT-create file and let the system service number being set there. You can set the system service number in the sample directly. A lot of different ways. And also from an implementation side, I mean, just if you get into this topic, it might be very difficult at the beginning, but if you understood this actually correctly, it's very easy. The only thing that, of course, we need to know here is where is those syscall instructions being located, and we have plenty of them in NTDLL. So it's very easy just to either rely on a fixed offset, which is possible, but not 100% of the syscall stubs that we have in NTDLL are look completely the same. The majority of them does, but some of them are a bit different, right? So you could either rely on a fixed offset, like this one here, it's in hexadecimal 12, or someone could just also simply pass the export table, get into each of those exports, and then just trying to find the syscall instructions. It's quite easy. From an implementation point of view, it's also quite simple. The only thing is we have the same code below there, we have the same instructions, but instead of calling syscall directly, we're just having this jump instruction, and we're jumping into an address which is basically, for example, for anti-create file at the offset of hexadecimal 12. And based on this, yeah, you can just simply make use of indirect system calls here. Well, this now brings us actually back to Pikabot again, and to something that, not fully sure if this is actually a valid official name, but we called it indirect random system calls. This is something that we have seen in Pikabot. What is this about? So we have the same setup as we have before with the indirect system calls. We have again our sample, we're preparing the syscall ID, and then we're basically jumping to NTDLL where we have the syscall instruction. The only difference here this time is instead of jumping directly to NT-create file, we are jumping to a completely different function which is called NT-create atom A, or anything else that you would like to have. So having a completely different function that we basically use, but we don't really care about all of those functions. The only thing we care about is the syscall instruction, because that's the most important thing we need. Everything else that is happening before, swapping around some registers, preparing the syscall service ID, this can still be done in the sample, because these are just some simple CPU instructions, and they do not rely at all on anything that is basically here. So this adds a completely new layer of confusion in the end, right? So just imagine if you somehow have a monitoring tool that's somehow maybe sitting between NTDLL and kernel, or maybe in kernel. So you basically come from a region that is for NT-create atom A. You would expect specific arguments that are being used for this function, right? However, and of course you would also expect a specific syscall ID, right? So then you go into the kernel. If you then inspect this stuff in more detail, we're actually having a different syscall ID, so it doesn't really match with what we can see here. And we are going to call NT-create file, right? NT-create file has completely different arguments to the function than NT-create atom would have. So this is not a point where this confusion starts to happen, because if an EDR or something else would start to analyze those calls that are happening, it tries to interpret the function arguments that have been passed to this function, right? And they don't really match anymore the expectation, and this actually seems to have caused quite some troubles with various different solutions when Pikabot actually started to make use of this. Yeah, and then basically we go to the kernel executes the stuff, and the kernel actually only is interested in the syscall service ID. It doesn't really care which function it was, because based on the ID, he knows what to execute. And the arguments are still there, because this has been prepared in the sample before. From an implementation point of view, this is actually as easy as the one that we had before with indirect system calls. We have the exact same assembly code below, but just instead of using the offset for NT-create file, we just use a different function. It doesn't really matter. It could be NT-create atom. It could be anything else that you can find in NTDLL. You just need, of course, to have the offset, because we only want to execute this syscall instruction. Well, and this is, as mentioned before, what we have seen in Pikabot. And to be honest, when we have seen this, we were quite surprised and impressed, because I think this is a very smart idea. Yeah? And for some reason, I was not fully convinced that the threat actors actually came up with this idea by themselves. Yeah? I think this requires some research, this requires a lot of time that they need to play around with this stuff. So there was a certainty of, yeah, I wasn't convinced that this is indeed coming from them. And due to a funny coincidence, we actually came across SysWhispers 2, which is just a well-known framework that is available on GitHub, basically. And after we looked into those things together, we just realized that this is completely the exact same implementation. So essentially, threat actors are also quite lazy, I think, and they probably just observed what is happening in the security community, figured out that SysWhispers 2 seems to be interesting, funny, and they just have taken this project, embedded it into Pikabot, and yeah, voila, you have basically quite a good evasive sample in the end. And it's somehow a bit scary to me as well that we have only figured this out in Pikabot. We've tried to search a bit through the web if there is any reference that malware actually makes use of SysWhispers, but we haven't found any information on this part. And due to another coincidence, actually, we came across an old Qbot sample, which I think was from May 2023 or even from 2022. I'm not fully sure on the date anymore, but it was at least more than 1 year old, which actually also had completely the same implementation there, which just highlights that indirect random syscalls, as we referred over here, have been used for quite some time already, but yeah, it looks like it was just pretty much uncovered at this time. And this is also one of the points where actually this confusion with direct and indirect syscalls starts to happen, because for us this is actually an implementation for indirect system calls. You never directly call the system call, you make use of existing instructions. The developers of SysWhispers 2, maybe we are wrong or maybe there's the confusion, the developers of SysWhispers 2 actually announcing this as direct system calls. So this is kind of the confusion that I've mentioned before. Well, now let's going back to the present and maybe even into the future. So this is what we have seen in Pikabot in the past, right? And of course, I've mentioned that before. Other threat actors they have already adopted those techniques. We have seen this in other families as well. So it's just out there, it's being used, even though Pikabot itself is dead. And this caused us to actually start thinking a bit more in the future. So if we have seen this, and this is basically coming from some open source project, what might be there that is already out there maybe as research projects that could be a potential target to be used by malware as well in the future? So we did a bit of research and looked into this topic a bit more. And one of those interesting things would be the combination of vectored exception handling and syscalls. So all of this, what I will show right now, is nothing that we have seen yet in malware and malware families, but this has been already researched, and it's likely to be a case that maybe the same thing with SysWhispers can happen in the future, and we will also see this. So what is vectored exception handling? Just a quick recap on this. It's a tool that you have on Windows that you can basically allows you to register functions that can handle exceptions that occur in your program. And this is actually very powerful, because if the exception occurs and your callback function supposed to handle the exception is being called, it allows you also to modify all of the registers, and of course this also allows you to completely change the control flow, right, as part of the exception handling, which is kind of ridiculous, because completely changing registers and the control flow might not be the initial intention of handling exceptions. Yeah, and this can also be used in this case, and we have experimented with this as well. So as an example, seeing our sample again here, we execute it, and at a specific time, basically we register our exception handler, and at a specific time we want to create an exception. There are various different ways how you can do this. It's either jumping to an invalid address, trying to read from an invalid address, having a division by 0, doesn't really matter. As soon as the exception occurs, we're basically going into our exception handler function that, yeah, the developer controls. And as we have seen before, for all of those syscall stubs, we can essentially just do the completely same thing again. So we're swapping the registers basically, or we're moving the values in the registers. We are preparing the syscall number, which was hexadecimal 55 in our case, for the ntcreate file function. And then we are setting the instruction pointer to any syscall instruction that we can find in entity.l again. In this case, we just used ntcreate atom again, because, yeah, it's a good example, and it's one of the first ones in the end. So an exception occurs, then the exception handler jumps in, and out of nowhere, the execution of the sample seems to be completely different in the end, right? So this is definitely not something that might be the intended use case of this, but you can see the power of vector exception handling. Also from an implementation side, this is quite easy. You essentially just register your exception handler. You basically have your exception handler function over there, which essentially just does what I've told before. It's basically re-implementing this system service, this syscall stub. It's moving the registers. It's setting the syscall service number, and then it's just changing the instruction pointer, the address pointing to syscall instruction. So that's actually quite easy. And yeah, it just works. And it probably adds another layer of confusion to tools that have to be monitor and understand and follow this execution flow, because this is, of course, then completely out of scope what would have been expected there. There is actually also already something out, which I think is called the mutation gate. You can also find this on GitHub, which is a similar approach, essentially. The only difference is here that they are not causing any exception due to some invalid addresses or whatever. Instead, they're just setting a breakpoint, a hardware breakpoint, in one of the syscall stubs in NTDLL, right? So considering our anti-create atom thing again here, the function, so you basically just register a hardware breakpoint on the syscall instruction over here. You call anti-create atom A as an official function, and then use the exception handler to adjust the already set system service number, and maybe also to adjust all of the arguments that you want to have. So basically completely play around with whatever you want, and when this is done, you just continue the execution. So this is, of course, the power of vector exception handling. Yeah, and another approach that we do have, of course, we all know it, is return-oriented programming, or ROP chains. It's being used usually in exploitation. If you have data execution prevention on the stack, of course, you can't execute a shellcode, so you want to play around with ROP. And you can also, of course, combine this with syscalls. Why not? Yeah, this is just a brief example how this could look like. So basically, you could build your gadgets out of NTDLL. You can collect them, essentially re-implementing the syscall stub that we've seen before that prepares all of the arguments, the registers, basically. You can chain them all together and then just execute them. And the difference here is actually that this might already look a bit different if you follow the core stack, or at least the addresses, because then you actually have, again, some quite of legitimate addresses, at least from NTDLL, again, somewhere on the stack. Yeah, the only thing that you need is a couple of different a couple of different gadgets. You can find them in NTDLL to prepare the registers, to set the syscall ID, and of course, we have plenty of those syscall and red gadgets available in NTDLL because they are usually around everywhere. You can prepare the stack layout, you can use this, and you can execute this stuff. The good thing and the good news is that just using any of those techniques that we have highlighted here today, or at least just using by one of them, this usually is, at least nowadays for modern security solutions, not able anymore to get around them completely without being notified or noticed. Because there's another technique which is, of course, inspecting a core stack. I've previously mentioned it before. So basically, if you see a legitimate Windows API call that starts with create file W, for example, you see the samples address. If you look into the core stack, then of course we have kernel 32 or kernel base, you have another kernel base, and then you go into NTDLL. So just by looking into the core stack, and for example, EDRs actually also passing the core stack nowadays, you can at least try to guess whether the chain on where we came to this API call is legitimate or not. In the case of indirect syscalls, we can see that we completely overjumped kernel 32 and kernel base, so we only get into NTDLL directly, which is quite obvious and easy to spot. And if we would use direct syscalls, of course, it's way more easier because then we would not even have the NTDLL stuff here. Of course, someone has already realized this and also looked into this stuff. So there's also, of course, the approach and idea of faking the core stack or core stack spoofing, where you can also use, again, a couple of different techniques to get around this problem. You can make use of vector exception handling, you can use hardware breakpoints again, you can ROP gadgets. The main idea behind this in the end is just trying to rebuild a core stack, even though you never went through all of these DLLs and these API functions, to let it look as legitimate as possible. So this is also already something I think that is quite good working, but as mentioned again, just using one of those single techniques is nowadays not enough anymore. Maybe for specific products it is, but for the actual well-known ones, it shouldn't be enough anymore, and it should be detected, basically. Well, and this now brings me to the takeaways. So I definitely won't cover this in a summary anymore because I think it's a lot of different topics that we had here, and it's also quite technical. But what is the most important things that we can actually take here with us today? First of all, I think it's definitely not a secret, and it's definitely interesting to see that the goal of threat actors is still to try to get around sandboxes, try to get around EDRs, try to get around AVs, so they are still always trying to evade all of these products. I mean, it's kind of obvious they're trying to stay undetected as long as they can. They're trying to slip through to cause as much damage as they can do. So this is still one of their main goals. We have seen the history of the use of direct, indirect syscalls, but at least it shows us that the syscall-based evasion techniques are completely on the rise. It's not only on the threat actor side, but of course also on security researchers, on Purple teams. This is an interesting technique that is being researched quite heavily, with the goal, of course, for us to find the gaps that we can fill in the future before threat actors actually coming across this and can make use of this. And yeah, of course, we live in the cat and the mouse game as usual since a very, very long time. So they are still trying to improve their implementations. They're trying to improve malware just to make our lives a bit more difficult. On the other side, it's also challenging and interesting probably. But we definitely see this sort of trend that is definitely going to continue. And one thing that is, I think, very important to mention is that if we want to be prepared for maybe what is coming in the future, like the syscalls, the vector, the exception handling, and so on and so forth, one of the greatest sources we can still have is, for example, Twitter, X, however you want to call it, and also GitHub, of course. Research is being published there. You can actually make use of this. You can follow it. You can try to monitor this stuff and being ready for implementations that maybe someone can up with, because there might be somewhere a gap. And then, of course, we can take advantage out of this. We can collaborate on this and improve our security solutions just to make these things that happened with Pikabot, for example, not happen again in the future. With that being said, that's the end. Thank you for your time, and also thank you for listening. If there are any questions, I'm happy to answer them.
Thank you. Let's take the questions from the audience here first. Oh, there are a few, but let's take the gentleman was faster a little bit. So the race condition was won here.
Hello, thanks for a great talk. About syscalls, does it make sense to evade them? Because if I believe modern antiviruses are hooked in the kernel, don't they?
Yeah, so modern antivirus systems and also modern EDR systems are usually already now part of the kernel, basically. There's also the more extensive Windows event tracing that can be used. So in the end, those solutions should be able to detect this stuff. But to be honest, I think this example with Pikabot has also forced a lot of vendors that might not have went this step with going into the kernel, because we all know the kernel is also a critical thing in the end, force them actually to go a bit deeper into the system to actually be able to detect this stuff, right? So in order to really detect this kind of things, you have to be quite deep in the system. But yes, if you be on the kernel side, it's actually quite easy to detect this stuff. And this is also the point where a single solution or a single technique we've mentioned here is not enough. Trying to combine all of them might have some good chances still to slip through to some systems, but usually not the well-known ones.
We will take the question. The gentleman was over there as well, in the red, the man in the red. You have to use the microphone.
Okay, one simple question about Microsoft Defender. Is it safe with default Windows? Or maybe you can recommend some? Thank you.
Yeah, so that's a good question. I do not feel in a position to recommend any AV solution or any EDR solution that might be good and bring you on the safe side, because that's a dangerous answer, I think. But I would say the majority of those solutions that are well known, like Defender as well, they have improved a lot in the past. And of course, they're also sitting very, very deep into the system, especially Windows Defender, I think, should be. So there is a good chance that it will at least increase your security, but saying that it's 100% security, this, I think, is a bit out of scope.
All right. I always ask a question from my side to the speakers. So before you jumped into the area of the return-oriented programming, I was listening and I was like, oh, this really resembles jump-oriented programming, where you call the gadget to jump. I mean, there's like call-oriented programming and so forth. And with the what you called with the exception handling, this sounds more like safe SEH or SEH bypass, where you intentionally trigger, right, and call to the frame. Now, this definitely depends on the libraries that are loaded and if the ASLR is enabled. Do you, in Pikabot or any other malware that uses these exploit development techniques, how do they identify the library, the location, or they're not going to the fixed, right? They don't go to the fixed address. So what are the techniques to actually derive this offset?
So they usually, nearly all of them actually just rely on NTDLL because this is a DLL that is usually loaded all the times, right? And there are various different techniques out there. You can just pass NTDLL, you basically get all of the offsets, you get all of the addresses, you can just walk through the exports basically. So they really just use what is there, right? They don't really try to load anything specific, they just try to use whatever is there. And then of course I think, especially for what we've seen in PKBot, they are heavily just make use of shellcode in the end, where I can just play around and pass all of this stuff just to avoid using any additional libraries that are not loaded by default in the end. Yeah.
All right, with this, let's thank the speaker, and you have deserved socks and chocolate.
Thank you. Thank you very much. Thank you.